Okay, so as I said, I ran out of batteries before being able to finish this problem, the solution to this problem. Let's continue. So we had already shown that S is an upper bound, so is an upper bound. It's an upper bound. And so that means that if we want to show that it's at least upper bound, we can proceed directly, or we can use the property, the characterization of least upper bound that was given to you a while ago. We're gonna go that route, and we're gonna use that to show that this is in fact the least upper bound. So if you remember what the property said, um, what the property said was that given any epsilon, if given any epsilon greater than 0, we would be able to find an element in the set that was bigger than S minus epsilon, then that would be the supremum. Then S would be the supremum. So to that end, let me just so to that end, let epsilon be greater than 0. Arbitrary. We pick any epsilon greater than 0. Again, by the Archimedean property, we know there exists, and in N there exists N in N such that I forgot a U here. 1 over N is smaller than epsilon. Which of course is still greater than 0. Right? So we know there's one N that satisfies this property. We know, however, that S minus 1 over N is not an upper bound. That S minus 1 over N is not an upper bound. So therefore there exists an A in the set A such that A is bigger than S minus 1 over N, right? Because if not, if we couldn't find such an A, then S minus 1 over N would be an upper bound. But by assumption, we know that S minus 1 over N is not an upper bound. But S minus 1 over N is also bigger than S minus epsilon. Why is that? Because remember that epsilon is bigger than 1 over N, which then implies that minus 1 over N is greater than minus epsilon. If we add S on both sides, we get this, right? Which is exactly what we have here. So then, yes, A is greater than S minus epsilon. Remember that we just gave ourselves any epsilon, and we show that we can find an element A that is bigger than S minus epsilon. So this means that S is the least upper bound by the characterization, right? So this means that by the characterization of the supremum covered not long ago, we can conclude that S has to be the supremum of A. Okay, I mean, in case we you've lost track of what we've been doing, so the original question says this: A was a non-empty and bounded above the subset of R, and we let S be in R, a number S in a number S, a real number, S have the property that for all n in n, S plus 1 over n is an upper bound for A, and S minus 1 over n is not an upper bound for A. We were meant to show that S had to be the supremum of A from this information. And we split this into two things, which allows us to show two separate things. The first one is that if we know that S plus 1 over n is an upper bound for any n in n, then S itself must be an upper bound. Now, the fact that whenever we subtract just a little bit, that is not an upper bound for A, this is an indication that S has to be the least upper bound, and we use this minimality here to show that that's the case. I mean, what we didn't know yet that this is a minimality thing, but this really sounds familiar to the property that whenever you subtract epsilon from S, you're able to find an element in the set is bigger than that. And if you know also that the number S, so S, if you have a candidate, say S for the supremum, means it is an upper bound, and whenever you subtract epsilon from that number S, you can find an element in the set that is bigger than that, then there is the least upper bound. And so that sounds very familiar to us when we look at, no matter how big n is, S minus 1 over n is not going to be an upper bound. So that ties in with that kind of minimality thing that I was alluding to. And so here's the proof. We said, of course, we can never find an element A in A that is bigger than S. Is for every n S plus 1 over n is an upper bound, because if a minus s would be positive for some number, then we would be able to put some 1 over n in between a minus s and 0, which would violate the fact that s plus 1 over n is an upper bound. So that shows the first part. In the second part, we just need to pick any epsilon greater than 0 and find a 1 over n that is smaller than that epsilon. And of course, 1 over n is going to be still greater than 0, but then that allows us to show that we can find an element in A that is bigger than this s minus epsilon. And that shows that then this is, by the characterization that we had before, that shows that this is indeed, S is indeed the least upper bound of the supremum. Okay, so next time we'll continue with some more applications, because the being able to being able to prove that involve the use of the supremum, or the straight that asks you to show that something is the supremum of a set, is very important in this course. Okay, so that's so we continue then for Thursday's lecture.